So let's dive right in with an example. In this case, we're going to try to find the equation of the line that goes through 2 points. So the 2 points will be -1, 2, and 4, -23. It might help before we get started just to kind of get a quick little sketch of what this is going to look like. So the point -1, 2 is going to be somewhere like here, just so that we can kind of see that. And then 4, -23 is going to be over here, but way, way down. So we should expect a line that has a negative slope, probably pretty steep. And this problem is different from what we've done before because I now have 2 points, which means I have 2 potential places to start. And I also don't have a slope, and that's what we had before. So the main question we're focused on here is what is the slope, or what is the rate of change? So as we go about writing the equation for this line, we need to start by figuring out our rate of change, because that's where we started before. So that's where we're actually going to start. So let's go ahead and stack our 2 points. So -1, 2, and 4, -23. The order, again, doesn't matter. So we'll do our change in y, 2 minus -23. So that's the change in y. And then we'll stack and subtract these, which is going to be -1 minus 4. And that is going to be our change in x. And 2 minus -23 is going to be +25. And -1 minus 4 is -5. So that can simplify down to -5 over 1, or maybe more simply put, -5. Okay, that is our rate of change, so our slope. So now essentially we have the exact same problem that we had before. The only difference is that we actually have 2 points that we can start from. So we have 2 different values of h and k, and either one is going to be totally fine to use. If we use this one, we'll do h as -1, and our current value of k is 2. Or if we use this point, our value for h is going to be 4, and our k value is going to be -23. I'm actually going to choose for this problem to use the smaller numbers, only because I'm hoping they might be simpler, but I don't really know until I try. So we're using the same form that we used yesterday, which is y equals k plus m, the rate of change, being applied some number of times. So x minus h gave us how many times we'd apply that same rate of change. And we know that k is, in this case, 2. So I'll replace k with 2. And we know h is -1, so I'll replace h with a -1. And then we're just going to copy everything else down. So y equals k plus, and then our rate of change for this problem is -5. So I'll make sure I put that in the place of m. And then it's going to be x minus -1. So that is ugly right now. There's some weird subtractions in there, so let's just clean that up a little bit. So y equals 2, our current value for y, plus -5, which would be -5. So our rate of change is that we're going to keep subtracting 5 every time x goes up by 1. And the number of times x is going to go up is given by x minus -1. So we could write that as x plus 1. This is the vertex form, or the form we've been talking about, of a line. And we can plug in different values of x, and we can easily churn out what the future values of y would be. So this can give us any point on our line. But often we like to write slope-intercept form. So let's go ahead and do that, which requires us just to simplify. So that's kind of the step 4, which is an optional step. And we're going to talk in the next example about why that's optional. So that would be 2, and then I need to distribute this -5 right here. So minus 5x, and then -5 times 1 minus 5. Simplifying that down, y equals 2 minus 5, that would be -3 minus 5x. Well, it was convenient. So if we look back at our picture that we started with, kind of visualizing this, that seems to make a good bit of sense. In this case, our y-intercept is located at 0, -3, and that's probably pretty reasonable, be right about there. In fact, the rate of change was to go over 1 in the x and down 5, and then we do it a few more times here. So essentially that x minus 1 part is just how much is this rate of change going to happen to locate some future point. And that can happen for any amount of points that are going to be on this line. And so the line is going to go down like this. That is our equation. So let's try all of this again with a different problem. In this case, we want to go through 2, 7 and negative 7, 4. So before we start, let's try visualizing this, and it's going to help us see some really crucial insights to our problem. So 2, 7, it would be located right here, and negative 7, 4 is going to be located right here. And we're going to notice that if we go ahead and graph that, we're going to end up with a line that goes through those 2 points. And I don't really know exactly how to graph it. I'll try to graph as straight as possible just by freehand, because I'm not really graphing the actual line right now, just getting a picture of it. It looks to me like that y-intercept is some number that is not a whole number. And that could be a potential problem if I'm trying to graph this in slope-intercept form or trying to create the line equation in slope-intercept form. So more to come on that in a minute. Let's go ahead and start with step 1, which is to find our slope. We do not have a slope. So we'll go ahead and stack our points. And in this case, I think I'm going to put negative 7, 4 first, just because it doesn't matter. I'm just picking it. And then 2, 7. So let's figure our rate of change. 4 minus 7 for the change in y. And negative 7 minus 2, that'll be our change in x. So just to refresh our minds on that. 4 minus 7 is negative 3, and negative 7 minus 2 is negative 9. So our rate of change is 1 over 3. That's our slope. And we should be able to see that. We get a positive slope when we drew the visual. So that's very reasonable. Looks like we're going up 1 over 3, up 1 over 3. Those are our independent and dependent variable changes. And in fact, we can see that as we do that, we simply skip right over the y-intercept as a whole number. And I would probably say that about 95% of lines aren't going to have a whole number y-intercept. So this is going to show why this form of an equation is so incredibly valuable. So here we go, step 2. Let's go ahead and just plug into our formula. So y equals k plus m times x minus h. And we know our value of m is 1/3, so we'll pop that in. And then we come down to finding out values of h and k, and we have to decide what we're going to use. Again, it does not matter which one you use. I'm going to pick h to be negative 7 and k to be 4. So k is 4 and h is negative 7. And we'll just fill everything else in. So x minus negative 7. Probably should have put that in parentheses. And then we have the 4 plus 1/3. So we're just replacing our known values. So it looks still a little ugly. There's a subtracting and negative, which is gross. So y equals 4 plus 1/3. And we're going to add 1/3 a bunch of times. And the number of times is going to be x plus 7. So if I know my x value, like let's say, for example, that I choose some point way over here to the right, I'll just go ahead and pick when x is 5, for example. Okay. If I wanted to figure out what the y-coordinate was, I'm going to just continually add 1/3 to this number 7. So there is 7, that's why it's plus 7, plus the 5. Okay, so that's the 5, that's the 7, that's why I'm getting 12 if I put in a 5 right here. 5 plus 7 gives me 12. And I'm just repeatedly adding 1/3. So that would be 12 times 1/3, which means that I'm adding 4. That is what this is right here. When I put in a 5, that gives me 4, and I'm adding that onto my current height of 4. So that just goes back and explains why this form is what it is. But if I get rid of that and I try to go back to writing slope-intercept, let's try it. Y equals 4, and then I'm going to distribute, so 1/3 times x, and then I have 1/3 times 7. Oh, shoot, that's a fraction. That's why I had that y-intercept up here that I didn't know. It didn't look like it was a whole number. And that's exactly what's happening here. So now I'm stuck, because what I'm going to do is I know that I'm going to have a plus 1/3 x, but I somehow have to combine my like terms, which are 7 over 3 and 4. So now I got to go back and do fraction addition. That's super annoying. Doable, right? Not too hard. 12 over 3 is the same as 4, plus 7 over 3. Okay, that's going to be 12 plus 7 over 3, 19 over 3. So technically then I got to come all the way back over here, and then write 19 over 3 plus 1/3 x. Like, what a pain to do that. Okay, so that's why this equation right here in this vertex form is actually incredibly valuable. I don't always, when I graph a line, need to start at the y-intercept and graph my rate of change, because I definitely can't actually plot 19 over 3. It's much better for me to start at one of my two known points and then plot just a rate of change of 1 over 3.